let us look at a synthesis that has path generation and for 4-bar mechanism. And graphical approach. If you remember, path generation is when it is specified that a point on the coupler is going to follow this path. Okay, that's all that is given. So that's called path generation. And I'll also refer you to some section in Ratan for this. So there are two parts to it. One is path generation without prescribed timing. So in this, what is given is a point on the coupler has to pass through, let us say, these points. Let us call this E1, E2, E3. Okay, that's all that is given. A point on the coupler has to pass through these 3 points, and now design the mechanism. Okay, so the method is first we choose fixed points. Let us say the mechanism we are going to make, which we are going to synthesize, let us label it like this: A, B, C, D. Okay, these are A and D are fixed points, and E is a point on the coupler which passes through these points. Okay, so A and D are fixed points here. So choose fixed points A and D. Okay. And then also choose point B1. Okay, that means location of B. See, there are 3 positions, position 1, 2, 3. So you can say B1, B2, B3. Corresponding to that, there is C1, C2, C3, and there is E1, E2, E3. So choose B1. Okay, so we have this freedom. So that is straightforward. And after that, we can locate B2 and B3. Okay, because E1 B1 equals E2 B2 equals E3 B3. You see, this EB, that distance does not change because these are points on the same link. So E1 B1, E2 B3, E3 B3, they are all same. So let us follow these steps first. So we can choose point A and D. Let us say I take point A is here. Okay, D is here. Okay, generally that is done because you want to choose the fixed link depending on the convenience. Okay, how long you can afford all those things, and choose B1. Let us say we take point B1 here. Okay. And E1, E2, E3, those are already given. So this is E1, E2, E3. Okay, those are already given. Now we will locate B2 and B3. How we will locate B2 and B3? See, point B is always going to be okay on this arc, because A is fixed, AB, this is going to remain fixed. So B will always be on this path. Okay. And BE is fixed. So you got B1, E1. You have this distance. And E2, B2 will be same. So E2, you take the same distance with compass you can cut. So maybe you get say B2 here. Okay. E3, B3, same thing. So B3 will be here. So like that. B1 and E2 B2 will be same as E1 B1, so you get B2 and similarly you get B3. Okay, so that step is done. Now we have A, D and B. All we have to do is locate the point C. Okay, then the mechanism is done. And how to locate C? Okay, to get point C, okay, you have to consider a kinematic inversion in which coupler is fixed. Okay, consider a kinematic inversion in which coupler is fixed. Okay, so if you fix the coupler, that means now AD is not fixed anymore and point D can move, and D will move. You'll have positions of D as D1, D2, D3. Okay, and A will also move, but B and E, they will not move. Okay, now how to consider this kinematic inversion, and we'll see how that inversion will give us C, point C. That is what we want to get. Uh, for that, you see, in position 1, let us just consider one position. Say consider position uh, 2. Uh, in position 2, the relative position of B, E and D, okay, that is like this. They form this triangle. Uh, Actually, this is not coming good here because the pen moves a little bit. But B2, E2D, B2, E2D. Okay, we have this triangle. And when we consider the kinematic inversion, then in position 2, this B2, E2D triangle, it may be oriented in a different way, but it will still be a similar figure. Okay, because kinematic inversion does not change the relative position of the things. It's kind of like the rotates the whole thing this way or that way. Okay, that's all it does. So B2, E2D. Now if we are considering an inversion in which coupler is fixed, so when you fix the coupler, then BE will not move because BE is on the coupler. So what you will have to do is make a triangle which is similar to B2, E2D on this BE. So effectively you are, I hope you get the idea. This triangle which corresponds to position 2, you are moving this triangle to base B1, E1, because we are considering a kinematic inversion. So what you have to do is B2, E2D and make a triangle which is similar to this, and let us call that triangle as B1, E1, and now D will move. Let us call that point as D2. Okay, so D2 will be, okay, let us say it comes say here D2. Okay, so this was D originally, we can even call that D1. Okay, then you got D2, and now we have another position B3 E3D. B3 E3D. So you have this triangle B3 E3D. So consider, so you'll have to draw a triangle which is similar to this, but on the base B1 E1. Okay. So and you can call that triangle as B1 E1, say D3. Okay, so wherever you get the point D3, let us say you get point D3 here. Okay, so see, what we did here is we got the position of point D when you have kinematic inversion in which coupler is fixed. Okay, and we got these positions by considering these similar triangles. We'll have to draw these triangles. Okay, these triangles we'll have to draw. Okay, okay, now let us see, go back to this mechanism here. If you fix the coupler, then D will move along this path. And now if we have three positions, let us say we have D1, we have another position here D2, and another position D3. Okay, so you are considering that coupler is fixed and D is moving to position D1, D2, D3. Then how can you get C? It is very simple, because distance CD does not change. You can take a perpendicular bisector of D1, D2 and perpendicular bisector of D1, D3, and wherever they intersect, that will be point C. Okay, so after drawing this, to get point C, let me just complete it here. Okay, you will take a perpendicular bisector of this. You can take D1, D2, and you can take D1, D3. Or you can take D1, D2 and D2, D3. Okay, whatever, does not matter. So you take perpendicular bisector and their intersection will be the point C that we were looking for, or more precisely you can call that C1, uh, corresponding to this B1 location, because we constructed the inversion for this position B1 E1. Okay, so what we will get is C1, and that's all. We got A, B, C and D. Okay, so this was path generation with graphical approach, and it is explained in Ratan, this section 5.6. It's a very short section, so you can go through this. And in this A is description of without prescribed timing, and the steps I already explained you. Okay, and there is another part to it which is with prescribed timing, so let us go through that also. Now what is given is, as previously, you are given E1, E2 and E3. Okay, so you are given three positions of a point on the coupler, and along with that more information about timing is there, that when it goes from E1 to E2, okay, then the displacement of the input link is theta 1, 2. Okay, this is also given, so it is with prescribed timing. Okay, and when it goes to point 3 E3, then the corresponding displacement of input link is theta 1 3. So there is additional information that is given here. So the method will be just as previously. We choose point A and D. Okay, now previously we also chose point B. Okay, we chose point B. We had that freedom, and then we located B2 B3, and that was done to get point C. Okay, now the change will be, we will not be able to choose point B arbitrarily because the timing is also prescribed. So only this step will change. Okay, how to get B, that will change, and after that we have to follow the same steps. Okay, so how to get B now? Okay, to get B, we have to consider a kinematic inversion with the input link fixed. Okay, with the input link fixed, and that will give us point B. Let us see how. So again, let us first just draw say this is point A, B, C, D, and this is the point E. Okay, so normally we have AD is fixed, and we are given, corresponding to this, we are given 3 positions of E. Say we can call them, say, E1. Okay, there is another position E2. I just want to put some points here: E1, E2, E3. Okay, now if we consider an inversion in which input is fixed, uh, how to get point B then? See, this point E2 comes by theta 1 2 rotation of crank, right, of the input link, because that theta 1 2, when there is theta 1 2 rotation of this, you get point E2. Okay, so if you want to keep the crank fixed, what we'll have to do is uh, the position of point E2, uh, uh, okay, how to explain this? Let me go back, sorry. uh, let us let me do this. Say this is position of B in 1, and say this is position of B at point 2, B2. Okay, this is E2. Similarly, we can have B3, E3. Okay, and this angle is given here. This angle here is theta 1 2. In going from 1 to 2, rotation is theta 1 2, and it goes from E1 to E2. Now for the purpose of kinematic inversion, now if AB were fixed instead of AD, then you'll have to lock the entire thing and rotate it like a rigid body so that this AB2 coincides with AB1. Okay, that's all you'll have to do, and you will get what will be the position of E2 if AB were fixed. Okay, so very simple. You'll do that by rotating AE2 in the counterclockwise direction, in this case by theta 1 2 angle. Okay, so let me write here. You rotate A E2, because point A we already chose and E2 is already given to us. We rotate A E2 by theta 1 2 in opposite direction. Okay, so that AB2 coincides with AB1. So effectively your input link is fixed then. And let us call that point as E2 dash. What you get is, let us call that E2 dash. Okay. So you rotate this thing by theta 1 2 in anti-clockwise direction and you get point E2 dash. Okay, similarly you can get E3 dash. You rotate AE3 by theta 1 3 in opposite direction. You get E3 dash. And now you can pause this for a minute and think how you will get point B. It is very simple. The answer is, if AB is fixed, then B will lie on perpendicular bisector of uh, E1 E2 dash and E1 E3 dash. So you take a perpendicular bisector of E1 E2 dash and E1 E3 dash, okay. And then point B will lie on their intersection. Okay, that's all. So you get point B, and rest of the process is same as in the previous case when the timing was not prescribed. Okay, just have to follow that. So let us go back to Ratan. So with prescribed timing, you are given point, referring to this figure 5.21, you are given point E1 E2 and E3. Okay, so first of all you choose points A and D just based on your convenience. Then you have to get point B, and how do you do that? You rotate AE2 in this opposite direction by theta 1 2, so you get E2 dash. And similarly you rotate AE3 by theta 1 3 in opposite direction, you get E3 dash. Okay, now you have 3 points, E1 E2 dash and E3 dash, and take their perpendicular bisector, and B1 will lie on their intersection. Okay, so this explains how you get B1. And after that the process is same as you do without prescribed timing to get point C. Okay, so this was path generation, and one example is also given here. Let us go through this. It says design a 4-link mechanism to coordinate the following 3 positions of the coupler point. So you are given E1 E2 E3. The positions are given with respect to coordinate axis. Okay, so positions are given like this. Think of these as coordinate axis, and for E1 E2 and E3 you are given the distance r and angle alpha. Okay, so like in polar form. So distance is 55, angle is 75, distance is 70, angle is 50. So like that you are given E1 E2 E3. And in this case timing is also prescribed. The angular displacement of the input link r, theta 1 2 is 30 degree, theta 1 3 is 70 degree. Okay, that is also prescribed. So what will be the process? Okay, same, you take point A and D arbitrarily, work out point B1, we already discussed that, and then get point C1. We covered that also. So you can go through this example and try to do it yourself. Okay, so that was graphical approach, and I'm not going to go through the analytical method, but I'll just refer you to this section. Okay, this section 5.10. Okay, So let us just go through this figure. These are the coordinate axes x and y, and you are given the three positions of E, let us say. Okay, E, its distance from the origin is r, its angle is alpha. So you'll be given r1 alpha 1, r2 alpha 2, r3 alpha 3. Okay, and let us say timing is also prescribed. Let us say it is prescribed. So corresponding to these, you are also given theta 1, theta 2, theta 3. Okay, that those will be the angles of the input link. Okay, that is what is given. Okay, so you draw this figure. These all these dimensions a, b, c, d, e, f. Okay, these dimensions have to be worked out. E is the point on the coupler which follows the desired path, and then equations are written for some loops. You can consider a loop here like this: o, a, b, e, o. Okay, for this loop an equation is written, then for another loop equation is written. Some variables are uh, eliminated from those, and then you get an equation which will have three unknowns, and you have there will be three equations corresponding to three positions of point E, E1, E2, E3. So you just solve them. Okay, so you can go through this section yourself. It's very simple. The equation is developed for the loop, and yeah, that's all, just 1.5 page. And once you have these analytical equations, those can be implemented in computer. It also gives a computer program to do that.